All right. Good afternoon, everyone. Welcome to Intro to Space Nav 2025, Lecture 27. And while I was intending to only do 26 lectures, there's going to be 27 lectures in this class. And this is it. Today's going to be kind of a half lecture, and then we're done. So Lecture 27 is going to be wrapping up our discussion of crater-based navigation that we started in the last lecture. So as a reminder, things have kind of been staggered a little bit. My hope was that visual odometry would be one lecture, but it looks like it was actually 1.5. So we talked about image features and visual odometry problem setup in lecture 25. Lecture 26 was visual odometry actually solving the math and then getting your answer, extracting your state info. And that's pretty much all you would need if you were doing homework 8. For those of you that are doing homework 7, crater-based navigation, we started by just kind of talking about, okay, if you have an image of the surface of the moon, you can identify craters and use those to navigate. Here's the 4 big steps. And we notice that they look a little bit like the steps of a star tracker if you squint. So the first is crater detection, which kind of mirrors the image processing that's done on board a star tracker. The next is we need some sort of a database of where the craters are on the moon. And then the next is using invariants. So we kind of, for a triplet of craters, we can come up with a kind of a numerical set of name tags and go, this set of invariants describes this set of craters. And then you end up with a database search, not unlike what we did for homework 4 when we were doing our star ID database search. And we just kind of went through the first 3 parts of this on Vibe. So I just kind of talked through crater detection, talked through crater databases, talked through invariant-based crater ID, and then also started to set up the spacecraft pose estimation problem, but we didn't get into any of the dense math. So today, we are getting into the dense math. So as a reminder, today we're looking into this relative pose estimation problem, which what this basically boils down to is we go through all of this rigmarole so that we can say these pixels in my image, this one, this one, this one, are these points in the world, this one, this one, this one. And this is going to sound a little bit familiar, right? If you have pixel coordinates and corresponding world coordinates, and you're trying to find the rotation between those, that is Waba's problem, right? That should sound a little bit familiar. That's where the relationship between the vectors in the first frame and the vectors in the second frame was a simple rotation. It's a little bit more complicated here. Here we're saying line of sight directions in my camera frame map to positions in my world frame, but you're also assuming that these are actual 3D points in your world frame rather than, points at infinity, the way that stars are, basically just directions. So we're actually left with what's referred to as the perspective endpoint problem, where we're trying to find our position and our orientation all from a set of points in 3D space and our line of sight to those points. That's basically what we're left with here. So this is crater-based navigation part 2, and we're, going right into the perspective endpoint problem. So how did I word it last time? Was it crater nav or crater-based navigation? Okay. Crater-based navigation part 2. Any questions about crater-based navigation before we get into the dense math? All right, cool. So we are left with the perspective endpoint or PNP problem. In this class, we will study one of the simplest solutions. You're going to laugh at me later because this is going to look kind of complicated. We'll study one of the simplest solutions. And this was proposed, if I could spell, in 1841. So 1841. You might think that's awfully old for a spacecraft navigation problem. Right, so the perspective endpoint problem is a surveying problem. Right, so this is something that surveyors have had to deal with for a long time. So this is the Grunert or Gruner, depending on your fanciness, TNP solution. I'm going to say Grunert. So here is the general setup to the problem. So let's just for kicks, I'm going to say that there's 3 points of interest. So here's 1, here's 2, and here's 3. And I chose them such that they form a right triangle. That's not necessarily true, obviously. This does not need a right triangle, but just for kicks, this is a right triangle. And then there's going to be some observer over here. That's the 4th point. So that creates this kind of tetrahedron. So you end up with, imagine a point here, point here, point here. I want to be clear that this is in 3D space, right? So these are 3 points here which form a plane. And then this lower left point is actually closer to us. Let's say that there's some world coordinate frame, which looks like X and then Y and then Z. And then from this point here, let's say that this is P1, and it's going to get really busy if I draw vectors from the origin to each of these. So just bear with me. We're just going to call this point P1. We're going to call this point P2. We're going to call this point P3. Okay. And really what we're after is R, the position of this point, but we're not even going to bother. I mean, I guess we can call this point R for now if we want to. That's fine. What we have access to is, stand by here, we have access to the line of sight vector from the observer to point 1, so we're going to call that E1. We have the line of sight vector from the observer to point 2, we're going to call that E2. And we have the line of sight vector from the observer to point 3, which we're going to call E3. Okay. We also know the world coordinate of point 1, point 2, and point 3. So that's pretty much all we've got. So this is given world points E1, E2, E3, and camera frame line of sight vectors E1, E2, E3. What are we after? Well, Brunner didn't actually pose this as a problem where we solve explicitly for R or for T. So what we're going to do is we're going to use Grunner's solution as a stepping stone to our solution, where what we really want is the rotation from the world frame to the camera frame and the position of the camera in the world frame. And that's what we're after ultimately. But what Grunner concerned himself with was side lengths. He said, let's treat this as a tetrahedron floating in space, where the distance between point 1 and point 2 is C. This is point A. This is length A. This is length B. And let's call the length between the observer and point 1, we're going to call that S1. We're going to call this S2. We're going to call this S3. So Grunnert was after, and by extension, we seek tetrahedron side lengths S1, S2, S3. And we're taking it on faith that if we know S1, S2, and S3, it's relatively straightforward to get the rest of the way to our position and ultimately our orientation, but one thing at a time. So let's see here. We'll start with mentioning this. The position of the world points in the camera frame is unknown. So we know that we're looking at this kind of triangle of points. we don't know, or I guess the observer at R does not know any of these distances, right? So you can imagine if here's your observer, you see one point along this line could be here, one point along this line could be here, and then another point along this line could be here. But I mean, it could just as easily have been here, here, and here. Like you don't know the positions, you just know the directions, right? I want to be clear about that. However, we do know the world coordinates of these points, P1, P2, and P3. And I'll say side lengths A, B, and C are frame independent. Okay, and we can also get angles between line of sight directions. Okay, so let's start with this. Clearly, A is going to be P2 minus P3 norm of that, right? It's the 3 to 2 distance, or the 2 to 3 distance, doesn't really matter. Similarly, B is going to be P3 minus P1, norm of that. And C is going to be P1 minus P2, norm of that. Fair enough. We also know we're going to define some angle alpha, where cosine of alpha is E2 dotted with E3. So that means that the angle here between 2 and 3 is going to be alpha, which I would label it on our original diagram, but it's going to get really busy really quickly here. And then following that same logic, cosine of beta is going to be E1 transpose E3. And then cosine of gamma is E1 transpose E2. Okay, so those are angles that we can get from things that we know, and these are distance that we can get from things that we know. So no shockers here. So we begin by setting up the law of cosines 3 times. It's wild that we can actually get most of the way through solving this just on high school math, which I think is pretty cool. So let's think about it this way. Maybe I'll zoom up a tiny bit so you can still see. So we're looking at the different sides of the tetrahedron, right? So we know there's one face of the tetrahedron where all the side lengths are known, A, B, and C, but there's going to be 3 other faces of the tetrahedron that we don't fully understand. And we can set up the law of cosine for each of those triangles. So we'll start with the 2 and 3 side, which I guess would be kind of the top face of this tetrahedron. And we can say that S2 squared plus S3 squared minus 2 S2 S3 cosine of alpha, here that I'm talking about alpha, is A squared. Okay, and then following that same logic, I'm just going to write these all out. We have S1 squared plus S3 squared minus 2 S1 S3 cosine of beta. That is B squared. And then we have S1 squared plus S2 squared minus 2 S1 S2 cosine of gamma. That's equal to C squared. And what we have here is 3 equations and 3 unknowns, where the unknowns are S1, S2, and S3. So you might say, why don't we just use, I mean, this seems to be a high school math problem, really fancy one, but we're using high school math techniques like law of cosines. My next high school math technique that I can think of is substitution, right? What about substitution and elimination and other systems of equations techniques that we learn about? Or what about change of variables, right? This is something we could do in that regime as well. And that's pretty much it. We're going to do a change of variables. We're going to do substitution. It's going to get gnarly, and then we're going to solve for one of the side lengths, and then the rest are pretty straightforward. So next, a change of variables. Okay. So we have S2 is going to be U S1, and S3 is going to be V S1, where all we're doing is we're just scaling. U could be greater than or less than 1. It could be scaling up or scaling down. Same with V, right? So these same three equations now become S1 squared, and then in parentheses, U squared plus V squared minus 2UV cosine of alpha is equal to A squared. And then we get S1 squared 1 plus V squared minus 2V cosine beta is equal to B squared. And then we have S1 squared, and then we have U squared plus 1 minus 2U cosine gamma is equal to C squared. And if we rearrange this, we get what? So you can imagine S1 squared is really A squared divided by the stuff in parentheses. Okay? So U squared plus V squared minus 2UV cosine alpha, but it is also B squared divided by 1 plus V squared minus 2V cosine beta, and it is also C squared over U squared plus 1 minus 2U cosine of gamma. Okay. And this is where we're going to skip ahead because it's going to get gory if we don't. I'll just say after some algebra or algebraic manipulation, we can solve for U in terms of V. And what we end up with is U is equal to, here we go, -1 plus A squared minus C squared over B squared, V squared, minus 2, and then in parentheses, A squared minus C squared over B squared, cosine of beta V. And then we have plus, and then in parentheses, 1 plus A squared minus C squared over B squared. And then all of this is divided by 2, and then in parentheses, cosine of gamma minus V cosine of alpha. Okay. So you might say, okay, big scary equation. Paul, I'm starting to get lost here. The whole goal is to be able to solve for S1, S2, and S3. Right? But we also just said that, well, okay, S1 is the square root of this stuff, where if I know U and I know V, we're done, right? Because everything else is known. We know A and we know alpha. Or you could say we're done if we even just know V, right? Because we could say B squared over 1 plus V squared minus 2V cosine beta. We know B, we know beta. Then we would know S1, right? You get the idea there. So the next thing we need to do is solve for V. And so I'll just kind of skip ahead for now. You can imagine that we have three equations, three unknowns. We're trying to do some substitution, rearrange, get rid of some things. I'm going to skip ahead and just say that further substitution leads us to a fourth order polynomial in V. Okay, and this is the really gory part. Well, not yet. We're going to call this A4 V to the fourth plus A3 V cubed plus A2 V squared plus A1 V plus A0 is equal to 0. That's our polynomial. Where, okay, first, I'm introducing the letter D, where D is A squared minus C squared over B squared, because that weirdly comes up a lot. It already came up 3 times in our equation for U. it's going to come up a lot in these terms that we're about to see here. So A4 is D minus 1 squared minus 4c squared over b squared cosine squared of alpha. Okay, not terrible. A3 is 4 d times 1 minus d cosine of beta minus, in parentheses, 1 minus a squared plus c squared over b squared cosine of alpha cosine of gamma plus 2c squared over b squared cosine squared of alpha cosine of beta. And you might say, please, for the love of God, tell me that A2 and A1 and A0 are easier. Nope, they're worse. A2 is 2, and then we get d squared minus 1 plus 2d squared cosine squared of beta plus 2 beta squared minus c squared, sorry, b squared minus c squared over a, ooh, careful, this is b squared, cosine squared alpha minus 4, and then in parentheses, a squared plus c squared over b squared, cosine alpha, cosine beta, cosine gamma, plus 2, and then in parentheses, b squared minus a squared, b squared, cosine squared gamma. That's the worst one. A1 is about as bad as A3. It's going to be 4 negative d times 1 minus d, sorry, 1 plus d, cosine of beta plus 2 a squared over b squared, cosine squared of gamma, cosine of beta, minus, and then in parentheses, 1 minus a squared plus c squared over b squared, cosine of alpha, cosine of gamma, and then A0 is 1 minus a squared minus c squared b squared minus, oh, that's all squared, minus 4 a squared over b squared cosine squared of gamma. Okay, there it all is. Give me a second to check my math, make sure I didn't just tell you a bold-faced lie here. A3 looks good. This is really bad, isn't it? Yep, A3 looks good. A4 looks good. Okay, unless I made a mistake in my handwritten notes, then this should be accurate. Now, if it's not, you can always go back and check the original Gruner. You can Google Gruner perspective endpoint problem, and I mean you can just look that up. This solution is publicly available. It's nothing that it's not like a secret that only I have access to. So while this is really gory, right? This is exactly the type of thing that computers were built for, right? Because we know the cosine of alpha, the cosine of beta, the cosine of gamma, A, B, and C, and then D, kind of by definition. So that means that we can construct A0, A1, A2, A3, A4, build this polynomial and solve, and it's going to be in no time flat, right? It looks gory, but it happens so fast. So this equation will, in general, have 4 real roots. Or I should say, it will have at most 4 real roots. It usually has 2. Okay. So you can imagine then that gives us 2 to 4 candidate values for V, right? It's like, okay, we found 4 different answers for V. If we know V, we know U, and if we know U and V, we know S1, and if we know U and V and S1, we know S1, S2, and S3. So this whole thing cascades from our answer for V, and there's 4 answers for V. What the heck are we supposed to do? And so my answer is we solve for all 4 answers, and then we go through and we check. We see what makes sense, which honestly kind of mirrors what we did last lecture for the visual odometry, right? There's going to be some ambiguity in your solution, but you can check and actually make sure that your solution works with the constraints of the problem. So for each candidate value for V, we carry on, solve the problem, and look at what I call reprojection error. So what do I mean by reprojection error? Maybe this kind of makes some sense. If you have V, you have U. If you have U and V, you have S1. If you have S1 and U and V, then you have S1, S2, and S3, which means you know all the side lengths of this shape. But then what if there was a 4th point or a 5th point or a 6th point? What if there were more points, right? Then in theory, if you were correct about your answer for your position and your orientation, you should be able to predict where the 4th point would be in your image. And then you can compute, well, how wrong am I? Am I off by just a fraction of a degree because I have some rounding error, or am I off by 90 degrees because I totally have the wrong answer, right? That's basically the idea. So a 4th point clears up the ambiguity in the perspective 3-point problem. But I kind of glossed over the whole solve the problem bit, right? So we have S1, S2, and S3. How do we find our position and our orientation? So let's say we have S1, S2, S3. How do we find R, which I'm going to say R is the position in the moon-centered, moon-fixed frame, and the attitude transformation matrix from moon-centered, moon-fixed to camera. Or you could just think of it as position in the world frame and then world to camera direction cosine matrix, right? How do we find those? So in this moment, we now depart from Greenwich solution and we're doing our own thing. Okay. So the position of the ith point, and I'm going to say this is in the MCMF frame, is equal to the position of the observer in the MCMF frame, plus attitude transformation matrix from camera to MCMF times, okay, what we're after next is, right, let's scroll up for a second. We're missing a vector here. Position of the observed point out here, P1, is going to be position of the observer. So if you'll forgive me here, I'm going to draw in red over this diagram. Don't trace over this diagram in red, just getting the idea across. This vector is this vector plus this vector. That's what we're doing here. So here's P1, here's R, and then, so this third one is what? Well, it's not S1 because S1 is a side length. It's not E1 because E1 is a direction. It's actually S1, E1. Or I'm even going to say SI, EI, right? The ith point is the observer location plus the attitude transformation matrix from camera to MCMF, SI, EI, where you could think of this part here as the relative position in the camera frame. Hopefully that tracks. Okay. So then if we were to take the subtraction of the two, and I guess maybe I'll just for kicks draw this. If you've got an observer R and you've got a point at PI, we're after, it's this side length, EI, it's SI. That's basically what we're saying here. If we subtract 2 points, I could say, okay, what is P2 minus P1? Well, that's going to be our position. I'm getting a little bit lazy with my frame notation here, so just bear with me. It's R plus T camera to MCMF. And then in parentheses, we've got S to E2 minus R minus T camera, MCMF, S1E1. You'll notice that the R's cancel out. So what we end up with here is P2 minus P1 is equal to T camera to MCMF, or you can think of this as camera to world, S2E2 minus S1E1. Okay. And what I would say is we're going to take this vector and we're going to normalize both sides. So you can think of it this way. S2E2 minus S1E1, that's really just the vector from point 1 to 2 in the MCMF frame. You can think of it that way. All right. So write it this way. Normalize the left side. We have P2 minus P1. I'm going to call this E12 in the MCMF frame. But if we normalize the right-hand side, we get the normalized S2E2 minus S1E1. And when we normalize that, I'm going to call this E12 in the camera frame. So to be clear, we're talking about not the vectors from the observer to the points, but the vectors between the points. Right? It's easy enough for us to find the direction vectors between the points. That's what we have on the left side of the equal sign. On the right side of the equal sign, we can find the direction vectors between the points in the camera frame. And maybe you see where we're going with this. So we could also say P3 minus P2 is equal to E23 MCMF, and then P1 minus P3 would be E31 CMF. Okay. And over here, we've got S3 E3 minus S2 E2 normalize is E23 cam. And then we have S1 E1 minus S3 E3 normalized, and that is E31 cam. And now we can say, okay, let E be E12 MCMF, E23 MCMF, E31 MCMF, and let A be E12 cam, E23 cam, and then E31 cam. And you see that basically we're left with Waba's problem, where we're only considering the vectors between points, not the vectors from the observer to the different points. But we can build the attitude profile matrix. B is A, E transpose. And then if we say We do singular value decomposition. We say U sigma V transpose is equal to B. And if we say M is a diagonal matrix, 0, 1, 0, 0, 0, 1, 0, 0, 0, and then we have determinant of U and determinant of V. So as we have this here, this forces our final answer to be a right-handed coordinate system. Then our answer would be attitude transformation matrix from the world frame to the camera frame is UM V transpose. So you see how it's very straightforward to find the position of the observer. There's actually 3 equations that will let you solve for R, right? But also, if you combine these equations and normalize both sides, you're right back to Waba's problem, and you've got this. T MCMF to cam is UM V transpose. And this allows us to solve for, now we have R, and we have T. And, I mean, we can basically just wrap this up now. So you can imagine this R and this T all cascade from one of our 4 answers for V. So we need to do this 4 times. We're going to end up with 4 RV combos. And so then finally, to actually score our answers, because we have 4 candidate answers, finally we say now what? We have a candidate pose solution. Pose, of course, means position and attitude. If a candidate pose solution for each real value for V, sometimes 4, usually 2. What we do is we choose the solution that minimizes reprojection error of the 4th point. Fourth or 5th or 6th, right? And 5th and 6th and so on. As many points as you have, right? We're assuming you have at least 4 points to solve this problem. So we would say, okay, Ti is equal to R plus T camera to MCMF, and then SIEI. But then what we should be able to do is say, okay, let's take T from MCMF to camera. So we're moving it around. Ti minus R. And if you normalize this, this should be Ei, right? That's the idea. So you should be able to compute the line of sight direction that you should see if your answer is correct. So I would say estimate E4 all the way up to En for however many points you have. And let the cost function simply be the sum of the squared error, right? Nothing we haven't seen before. J is equal to the sum over all points starting with 4. So it could just be 4. Maybe there's only a 4th point. Maybe there's 6 points. I typically recommend 5 or 6 points on homework 7. And this would be the inverse cosine of EI estimated transpose EI measured. And then squared. And that's it. So our whole PNP procedure to solve homework 7 looks like this. 1, compute A, B, C, alpha, beta, and gamma. Number 2, compute A0 all the way up to A4. For 3, solve polynomial for all real values of V. And then step 4, for each candidate V, step 4a, compute U, then S1, S2, S3. For B, solve for position and attitude. For C, predict line of sight vectors to points 4 through N. And finally, step 5, keep candidate solution that minimizes the sum of the squared reprojection error. And that is our PNP solution. Questions on PNP for homework 7? Feeling okay? Cool. So, good news. This is it. And I don't mean this is it for the lecture or for homework 7. I mean, I'm now done downlinking information to y'all. I am done lecturing. There is no new information. You know everything that you need to succeed on homeworks, all the homeworks, hopefully your projects as well. Yeah, that's pretty much everything. I'm good to wrap up the lecture. I have one last kind of my parting words of wisdom for everyone, because I feel like all the best professors usually have like a little heartfelt speech for their students at the end of the semester. And then I'm good to wrap up. So, any technical questions, or is it time to get all poetic and sappy? All right, cool. I'm hearing no objectives. Time to get poetic and sappy. So give me about, shouldn't even be 15 minutes. I want to share some thoughts with y'all. There is, I talked about getting poetic and sappy, but I'm literally going to read a poem that I found about 2 years ago that I really, really enjoyed, that I think that people can get a lot out of. And it has some life advice that goes along with it for anybody that wants to work in aerospace or wants to work at NASA or anything like that. I want to read a poem that I found called The Learned Astronomer by Walt Whitman. This is written from the point of view of a frustrated student who's tired of learning about astronomy. When I heard The Learned Astronomer, when the proofs, the figures were arranged in columns before me, and I was shown charts and diagrams to add, divide, and measure them, when I, sitting, heard the astronomer where he lectured with much applause in the lecture room, how soon, unaccountable, I became sick and tired, till rising and gliding out, I wandered off by myself in the mystical, moist night air, and from time to time looked up in perfect silence at the stars. And I really like this poem. It definitely speaks to me. It's one that's worth reading again and again, because my first thought is I have a really easy time self-inserting as the student, the kind of the protagonist of the poem, right? Because, all of you are RPI students. All of you have probably been frustrated students in lecture halls before. And this poem seems to point out the dichotomy between knowing something in the academic sense and knowing something in a more meaningful sense, right? You're kind of like, is it more important to know the equations behind astronomy, or is it more important to appreciate the true beauty of the universe? And I think this poem kind of paints the professor as an old fuddy-duddy and the student as somebody who still has a love for the world around them that hasn't been crushed out of them. And that's great. And I think when you read this poem the first time, that's the way it'll sink in. But then I read it a second time and I'm like, wait a minute, am I the learned astronomer? I mean, look at this. Like, this sure looks like the columns and the charts and the diagrams. Like, you can go to any one of these lectures. It kind of looks like I'm the bad guy in the poem now, where I've become the learned astronomer who knows all these charts and facts and figures. And I will admit that as you get older, it gets harder and harder to see the beauty in things that is so obvious when you're younger. It does actually get tougher and tougher. So I thought, which one of these people is me, Paul, and then which one of these people is you, the student? Are you the student or are you the astronomer? Because I mean, you're students now, but give it a few years. It's like you'll be professionals. Some of you might be academics. Some of you might work at NASA. Some of you might work in aerospace somewhere else. It's like, at what point do you become the old fuddy-duddy where you have all the numbers memorized, but the beauty of the stars and the universe and creation is lost on you, right? And the answer is hopefully never. I think that a well-rounded engineer is both of these people. What I mean by that is you need to have that little kid energy of, oh my goodness, I'm so lucky to be at this job. I'm so thankful for the position that I'm in. I'm so thankful for the incredible work that I get to do. But also, if you aren't completely intimately associated with the proofs and the facts and the figures and the columns ranged before you, you're not going to the moon, right? So think about the people that did the moon landing. Think about the greats. Think about, George Low, former RPI president, director of the Apollo program. I think everybody looks up to him. He had to be somebody who had the facts and figures all memorized. And, the flight directors and the engineers that designed the vehicle, they had to be numbers people. Otherwise, you never would have gone, right? It's like art and poetry is beautiful, but art and poetry doesn't put people on the moon. But then when you go to the moon, kind of paradoxically, art and poetry is what you get, right? All the astronauts, all the Top Gun macho fighter pilots that went to the moon, when they came back, all they wanted to do was write poetry and write books and talk about what they've seen. And some of them felt differently about God and the universe and all that. And it's incredible what happens to you up there. So I think it really is important that you are both of these people. And so I want to encourage you. Some of you are going to graduate school. Some of you are going into industry already. Even if you're not going into aerospace, if this is just a class that you're taking for fun on the side, which this is a heck of a tough class to take for fun on the side, you will need to become an expert at the proofs, the figures ranged in columns. But if you lose the meaning behind all of it, then you lose your soul, and there's no point to that, right? So you need both. So anyway, that is my parting wisdom for everyone. And with that, I'm going to wrap up the lecture, but I am sticking around for an extra long office hours because I recognize that homework 5 is beating the heck out of people. So thanks for coming to my TED Talk. I'm going to wrap up here.